For question 5, it's very similar to question 4, just more insertion exercises. So let's say that I'm inserting 5. I'm looking at part A. So basically, we're doing different conversions from LLRB to 2-3 trees and then 2-3 trees to LLRB. So it's going to give you both one-way transformations. So for part A, inserting 5 into this current 2-3 tree, well, let's first figure out what this 2-3 tree corresponds to for a red-black tree. That's just 1, right? It's black because it's the root, and that's the only node that is in the 2-3 tree. So after we insert 1, right, we just have this 2 key node, and this 2 key node is going to be 5 and then 1. Okay, and the reason for that is because we want it to be left-leaning red-black tree. Okay, so in order to be left-leaning, the red node has to be on the left. And so while satisfying the BST invariant, right, of the node to the left, basically the left children being less than the root, if we want it to be left-leaning, then we have to arrange it so that the 5 comes first, and then 1 is the left child of 5. Okay, for part B, we want to insert 6 into this 2-3 tree. Okay, so now it's a matter of deciding where we need to insert. The same thing as with BST. So we walk from the root, okay, 6 is bigger than 5, so we need to go to the right child, and we need to insert it somewhere here, right? So let's say that we're going to insert it into, we are going to insert it into this node, but then this is gonna, oh, actually, sorry, let me actually draw the red-black tree corresponding to this. So we're gonna have the root be a black node, then we're gonna have a black left child, we're gonna have a black right child, because remember, if we had a right red child, that's gonna be one of those rotation cases, because now it's right-leaning instead of left-leaning. And then we're gonna have a red left child, which is 7. Okay, so now what happens when I insert 6? I know that I'm going to be inserting into the right leaf node, so it's going to look something like this. Okay, but now this is breaking the invariant, right? So I need to push up something. Let's push up the middle node. That's traditionally how you push up. So if you push up 7, you get 5, 7 here, right? And this has to have 3 children. So actually, let me just go back to how it was before. So after I pushed up 7, this is my new node, right? What happens is you do the splitting. So you basically split this in half. And so now your children consist of 6 and then 9. So this is what the splitting and the pushing up looks like. And what LLRB does this correspond to? Well, again, we have a 2 key node, and we said that a 2 key node would always be converted from here to here. So that means that I have a 7 as my black node, which is also the root. So it has to be black. And then my 5 as the red node. So it's going to look something like this. Then I'm going to have 1 here. I'm going to have 6 here. I'm going to have 9 here. Okay. So another way to interpret what this signifies really is that the red node is part of the same key as the parent black node, right? And so they really are, if you look at the 2-3 tree translation, 1, 5 are in the same node. So that's basically what it means. 5 and 5 is going to be part of the same node as 7, and it is. Now lastly, let's look at inserting 2 into this 2-3 tree. Okay, so first let's actually translate this into an LLRB. So again, we have the root be 6, and we're going to have it a red left child, and then this is going to have a black left child, which is going to have, a red left child. Okay, so basically this is corresponding to this, and then this is corresponding to this. Then we have 5 branching off from 3, and we have 7 branching off from 6. All right, so if we want to insert 2 into this, then this is really just a matter of comparing at each level the node to the value that we want to insert. So, okay, so we get down, so we know that we always want to insert at a leaf node, right? We don't want to insert it in the middle of a tree. So we're going to be inserting it in here because 2 is less than the keys 3 and 6. Okay, this is our new tree. But again, notice that it breaks the invariant of having at most 2 keys. And so we need to push up the 1. So 1 goes here. Okay, and this means that we split 0 and 2. And notice that this satisfies the invariant of 0 being less than all the keys, 2 being between the first 2 keys, and 5 being between the second 2 keys, and 7 being greater than all the keys. Okay, well, notice that there's still a dissatisfying node, right? Because we have 3 keys for the root. So now we need to push up the 3 to be a completely new root by itself. So now we have 1, 6, and then 3 gets pushed up. And again, we just split 1 and 6. And they each become a child of the new root 3. And so what LLRV does this correspond to? Well, it is actually exactly the tree that we just drew. Okay, so there's no red child in this case, because red child comes in when you have more than 1 key in your node.